And he will start
Possible work
next.
here. There we go. And we're going to share this out. Don't need to share this out. There we go. So I'm looking over the chat to see some of the answers that were given to that first question. And I see it all over the board. And that's great. I see a lot of JavaScript, a lot of the Unreal Engine. It's a very cool thing to play with. A couple of folks that are beginners in Python, a few that have been experiencing it before. But one answer caught my eye in particular, and that's someone that had been working in Python, but I tried using some of the NASA data sets and found it a little bit difficult. So I'm hoping you're going to be pretty excited by this, because I'll show you that it maybe is not as difficult as it seems at first. The thing about coding, any kind of coding, is you never want to be reinventing the wheel. You want to take advantage of what others have done. And I'm going to be sharing with you, in particular, a library called Skyfield, created by a gentleman called Brandon Rhodes. And he used, I've used his libraries for quite a while to do astronomical type coding. Prior to that, there was a library called PyFM, and the FM stands for ephemeris. And we'll dive into that in a moment. But you never want to reinvent the wheel. One of the things that the folks that invented Python say over and over again is don't repeat yourself. So that's important, regardless of whatever language that you are working with. And if you are a scientist, want to be a scientist, or even if you're doing something else, everybody needs to know how to code to some level. You know, maybe you're not going to be doing this kind of coding, but even knowing how to use Excel spreadsheets and knowing how to use them well is going to make your job a lot easier. You want to automate the boring stuff. There's even a Python book called Automate the Boring Stuff. It lets you get to the much more interesting things a lot quicker. So what we're going to do here, I'm going to show you two simple scripts, simple programs that are going to answer very specific questions. Martha mentioned that I contribute to WRAL either online or I go on air from time to time, particularly the weather department, and that's with answering astronomy questions. And that's really what this comes down to, is answering questions. Questions can be as complicated as, you know, what's the best way to see Comet Neowise back last summer. I've spent a lot of time coding up some Python scripts that allow us to predict when and where was the best time to see that. And that was pretty involved. Or it can be as simple as I got a phone call early October last year, both from WRAL and several other folks in the media, friends that I have across the country. Started hearing about the full moon on Halloween and hearing that that was rare. And just how rare was it? I actually used Skyfield to answer that question. And some ephemeris, some data files from NASA I downloaded that went back 30,000 years to be able to answer that question. So that's what's going on here. I've been told that I am the only AP writer, quote unquote, to ever have links to source code in my stories, in my science stories. You always want to share your work because it helps others to build on it and keep you honest to find things that you've done wrong. So this is what we're going to talk about today. What's coding? I'm going to talk about some of those tools that are available. We're going to do a live demo, actually two of them, and then where to learn more. Go ahead and throw two of them up here right now. The question I get the most often is, how do I learn Python? Python is one thing that you can learn. It's really, really popular in the sciences, particularly in astronomy. It's getting very popular in data science. It's pretty good at reducing data sets, regardless of the science, and also in artificial intelligence. So I'm going to make a lot of use of Skyfield, and this is what that is. I'm also going to make a lot of use of NumPy. NumPy is a package that does a lot of things with numbers and does them very efficiently. Skyfield is all about bringing in data sets, live data sets, be it a star catalog that tells us where the stars are in the sky, bringing in these ephemeris, and I'll show you in the next slide what that exactly means. It tells us where the planets and the moons are in the sky. It does almanac functions, which helps us understand the seasons, sunrises, sunsets, the lunar phases. Used that a lot when I was trying to answer that question about Halloween, because it was all about the full moon. Timescales are super important here. Time is weird. We have this idea that time is, we use it every day. We use our calendars every day. So we're kind of used to that. But when you start working with astronomy and time, you come to understand that there's lots of different timescales that are going on. I mostly work in what's called terrestrial time, meaning the wall clock we have here. But there's a couple of different coordinate systems you have to deal with. That's what I'm talking about down here. There's topocentric, which means your observer is standing on the surface of the Earth, and you need to describe where that is. So, Raleigh here on the surface of the Earth. There's some things in astronomy that are the same no matter where you are on the Earth. We call those geocentric. The moon's phase is an example of that. The moon turns full at an instant in time that is the same throughout the Earth. Now, when the sun rises is different in Raleigh than it is in Asheville, is different than in San Francisco. So that's a topocentric one. And there's other centrics. Heliocentric means it's sun-centered. Selenocentric means it's moon-centered. There's bunches of them, but we're mostly going to be working with geo and topo here. Like I mentioned, you can pull in stuff from the star catalogs. There's a couple different ones out there. The Minor Planet Center is how we work with asteroids and comets. So a couple of weeks ago, there was a comet that was discovered that's starting to generate a little bit of buzz. You may or may not have read about it. I wrote about it in WRAL.com. You can go look that up there. But there was not a whole lot of information about whether it was going to be visible, just that it might be visible come December timeframe. So pull its orbit in from the Minor Planet Center, run a little Python magic on it, and determine that, yeah, it might be visible. If it survives, comets can break up. It's a long way away. But if it survives, it will be possibly naked eye visible low on the horizon. That's all possible using this. So I mentioned ephemeris. I want to explain the word a little bit and show you where we're coming from it. You go back hundreds of years ago, and we've always had tables that describe where the planets are in the sky and predict where they will be on any given day. It's actually how astronomy started. Astronomy started by the European royalty, in particular, paying scientists at the time to generate charts for astrological reasons. But those early astronomers were happy to have their research funded doing these things. They built these tables. Well, you fast forward to 60s, 70s, and beyond, all those things have been digitized. It's a series of very complicated math formulas that are all behind the scenes here. You can order it on a CD if you're super old school. I just download it, and you'll see where I download it. And the string of hexadecimal numbers that you see there, that's actually what one of the files looks like. I dumped that out of the very file I'll be using. And it's figuring out all of this trigonometry that you see down here on the left-hand side. But they're called ephemeris or ephemerides. They're downloadable straight from the Jet Propulsion Laboratory's website. I don't even have to worry about the address of where I download them from because Skyfield takes care of that for me. So let's jump right into things. First thing we're going to do is we're going to build a star chart using Python. So over on the left-hand side, this is Sky Maps. You can go to skymaps.com and download this once a month. And it's a great little resource that shows you where things are in the sky. But one of the challenges whenever you're trying to represent the sky is you're trying to represent what we call the celestial sphere. It's this imaginary, kind of sphere that encases the Earth, and we picture the stars as being on this sphere. If you've ever been to the Moorhead Planetarium or a planetarium like that, the best way to represent the sky is a dome. But if we're printing a book or if we're trying to do something on a two-dimensional computer screen like this, you got to make some choices. So here's my choice over here. I'm going to use Python to pull down a star catalog and use another piece of Python software called Matplotlib to actually plot it as if it were a scatter plot. And you see that some of the dots are a little bit bigger than others. I've represented the brightness of the stars by making the dots bigger or smaller. And that's how our eyes tend to see it. So I'm going to use the Hipparcos star catalog. It's one of many, but there's 118,000 some stars in that catalog. And it ends up, here's all of the constellations that are going to be pictured there. Problem is, if I were to show all of those, go ahead and plot all of those, it would just about turn white. There'd be so many dots there, and that's not really useful. And you'll see throughout this demonstration that we do something, And then we refine it, refine it, refine it until it answers the question that we were asking from the start, makes it more useful. Over here on the right-hand side, what this is, it's showing relative brightness. So we call it magnitude. It is a logarithmic scale. So when you go from a 0 to a 2 to a 4, you're not just jumping 2, you're jumping much, much more than that. The brightness increases and decreases really, really quickly. It's a flip scale. So the lower the number, the brighter the object. The sun's a -26, the full moon's a -12, just to give you some idea of what we're looking at here. The human eye tops out at a little bit more than a 6. We've got a couple of dark sky sites throughout North Carolina, and there's one up just over the Virginia border that can get close to that point where you can see high 5s, low 6s, rural North Carolina around a 4. Downtown Raleigh, we're rocking about a 1.8 on a good day. Certainly not right now with all the rain and such in the forecast, but know that that's where those numbers are coming from. We're going to use that Hipparcos star catalog, and we're going to use the data that comes out of that has an address for where that star is. It's kind of like an X and Y coordinate if we were to take that sphere and lay it out, but we call those line of right ascension and declination. And you'll see those on the chart. So this is the code, and I'm going to drain this pretty quickly, and we'll get into a little more deeper demo on the next set of codes. I'm going to pull from Skyfield a couple of pieces of software that I need. I'm also using specifically this Hipparcos star catalog. I mentioned I was going to use Matplotlib to actually do the plotting. This section right here, it's all about setting up the graph. My x-axis is that right ascension address. My y-axis is a declination. I'm going to set my limits here to 7 and 4. So I'm picking just a part of the sky. I only want to display just a part of the sky. The smaller the part of the sky you use, the less distortion. Because again, we're trying to make something that's really three-dimensional and represent it two-dimensional. I'll draw a couple of lines there so I can keep track of things. With load.open hipparcos.url. This is the URL that's stored in Skyfield. I'm downloading the star catalog here and load it into what's called a data frame. It's just a way of representing it. It makes it easy to filter. I'm also going to load from the Jet Propulsion Laboratory, NASA's Jet Propulsion Laboratory, one of those ephemeris that I described before. DE stands for developmental ephemeris. This is the same set of data that NASA uses to plan missions, to plan the trajectory, to plan the how they're driving those spacecraft through space. And there's a number of them out there. They vary by how much accuracy they have for particular planets. They've redone them for Mercury when we sent the Messenger mission out to study Mercury. One of the most recent ones that was created was specifically to add some additional resolution to the data for Pluto for the New Horizons mission. But we need Earth here in order to do that topocentric. Actually, no, this one's geocentric, that geocentric view. And here I'm starting to do my filtering. So I'm going to say 5. We're going to look at any star that is less than about a 5. And then I create this bright stars variable. And this is where Skyfield is doing that observation. It's figuring out what the right ascension and declination is. And there they are being dumped out. It actually figures out the distance too, which could be useful to you. And to take just this couple of sets of lines of code, all I need to do to create this over here, let me throw it in this mode. There we go. And create the graph that you see, or the chart you see over on the right-hand side. And this right here, this table that I just threw up, that's what the Hipparcos catalog actually looks like. It's a bunch of numbers. That's the nice thing about something like a Skyfield. Let somebody else do the hard work for you and build off of that. That's what science is about. It's not about starting from square zero. It's about building on what others have done. I figure out the observations. I pass it to Skyfield. I'm sorry, I pass the Skyfield data to the matplotlib, and I plot my my chart, and I create Orion. So you can do some really cool things in just a few lines of code. So I'm going to pause there and see if there's any questions before I jump into the next section, where we're going to look at how the apps that you may have on your phone, and there's a couple online as well, that tell us when the International Space Station is going to go over. We're going to build that and for ourselves and understand how those work behind the scenes.
Thank you, Tony. So from G.N. Murphy, can you import NEA data, and is Ephemeris part of Skyfield?
Ephemeris is not part of Skyfield. That's the neat thing about Skyfield is it's a helper for all these great data sets that are out there to be pulled in. And it's important because those data sets, they update all the time. And we'll see that with the ISS in a moment. It updates several times a day, even for some of the satellites. So it's important that these tools give us the ability to use the most recent data.
Thank you. And then Juliana wanted to know, is there a GitHub repo?
You're way ahead of me. Last slide, I'll share my GitHub repo
Thank
with you. And if you wanna read ahead, it's GitHub/RTP, which we should all be at least familiar with. Hokie, H-O-K-I-E.
Okay, thanks.
So feel free to jump on that if you like to. I share absolutely everything that I publish for WRAL and everything I'm going to publish here. As soon as we get done here, I'll push the code up there, and you can have at it.
Thank you. Yes, it looks like they might have joined a little bit late, so
no worries.
No worries. They missed it. Okay, and then Crit3 wanted to know, can you explain how you made Orion? I guess maybe they mean from like code to picture.
They might be referring to this set of lines that I put right here. That code isn't displayed here.
Okay.
But that's when you specify what the important stars are.
Okay.
And the way to do that programmatically is constellations are like neighborhoods in the sky. And they are official. The International Astronomical Union defines where those boundaries are, where those neighborhoods are. And the stars that make up the pictures that we see in the sky, or we see in books that we're supposed to see in the sky. Some of them make a little more sense than others. Those are pretty much based on the brightest stars. So programmatically, you could draw these lines by connecting the stars that are brightest. That would be how you would do that. And the names, some of those are in the star catalogs. Most stars within a constellation are named by their brightness. They're named by the constellation. So the brightest star in Orion would be called Orion Alpha. The next brightest star would be Beta. But some of them have Arabic names, the more prominent ones, the brighter ones. I've shown a few of those here. Some of those show up in some star catalogs, some don't. It's a good question.
And so then that the lines then is in your program, and you're telling it to connect the dots essentially. That was another.
Yeah, that does. To be clear, that doesn't appear over here.
Right. It's part of your code, though. Okay.
That can be coded, yeah, as can be the labels and everything else. That can be coded.
Great, thank you.
Yep. So moving on, we're going to spot the ISS. And we're going to do it again step by step by step. So let me give you a little bit of background of how this works. So the ISS is in orbit around the Earth, and it is in a nearly circular orbit. I'll prove that in a moment, but not completely. So to know when the ISS is going to be visible, we need to know a couple of things. We need to know what shape its orbit is. We need to know how high it is above the Earth, because that tells us what the footprint beneath it is. You know, that what's the circle imaginary circle that moves along with it. That when you're within that circle, you can see the station. We need to know, is it going to stay in that orbit? How does that orbit change? So these numbers down here, this is called a two-line element set. This is something that's downloadable from NORAD, and this is what the iPhone app or Android app or whatever you're using is doing. Uh, if it's a well-built app, it's only doing it every couple of days. This does change, but for our purposes, you only need to download it every couple of days. And it uses this right here to calculate based on your longitude and latitude, which your phone should be able to tell it when the station is going to go over. So I'm going to pick this apart because I actually find this quite fascinating what numbers are going on here. The first part of it, these are all just identifications. The satellite number, the international designator. The international designator, I'm sorry, the satellite number is an incremented number. Every time there's a launch, this goes up by 1. The letter next to it designates, there may be 1 or more payload items, satellites that can be put into orbit by that particular launch. So that goes up A, B, C, D, E. That gets really big when we start talking about some of the SpaceX launches that happened recently, where there's dozens and dozens of satellites that go up. So that keeps going up. This is what's called an epoch time. So that is when this particular measurement, and I just downloaded this from NORAD this morning, right before we jumped on the call, so I'd have an up-to-date one. You can read it this way. 21 is the year, so 2021. 030, it's the 30th day, so this was updated last night, actually yesterday around noon UTC, noon Greenwich Mean Time. That's called a Julian date. Time and dates get kind of cruddy when you're working with them in software. So we want to be as simple as possible and do it the same way. So when we are converting, we only convert once back into that kind of human readable time. So what you're seeing here is the 30th day of 2021, and everything past the decimal point is describing a fraction of the day. So it works out to this: 12:01, 55 seconds, and a 0 shouldn't be there. .1634, and so it shows a fraction of a second. But by representing this as a floating point number in the inside the computer, inside the software, it keeps us from converting back and forth between hours, minutes, and seconds, and rounding errors and things like that. So we always work in this. And you notice that this is in, I don't say it here, but it's in UTC, it's in Greenwich Mean Time. This is, we're going to be talking about a topocentric observation when you see the station is different in Raleigh from San Francisco, but we always work in UTC and then convert it back at the last moment. So the next part of this is inclination and right ascension. That's what's going on here. Orbital inclination is this angle right here. This is 0, this is 90. So this particular one is 51.64 degrees. That tells us the shape of the orbit and where that orbit happens. The other part is right ascension, and you saw that back in the star catalog. Again, places it in space. The next thing we're going to worry about is the number of orbits per day. So almost 15 and a half orbits per day for the International Space Station. That tells us about its speed. And if you do the math on that, you're going to find out it's right about every orbit takes 90 minutes. So every 90 minutes, the astronauts on the International Space Station are be able to see a sunrise and a sunset, which is kind of cool. The next part that we worry about is eccentricity. That describes the shape of the orbit. Eccentricity of 0 gives you a perfect circle. An eccentricity of 1, that's pretty much a line. So this is a very small number. They've omitted the decimal point here for space. But you see this is a very, very small number, so it's almost a circular orbit. Perigee, that's how far it is above the Earth. That's its altitude at the closest point. Apogee would be the farthest point. Anomaly is about wobble and things like that. This whole section right here is about changes. Now, the International Space Station is up there orbiting at about 250 miles above the Earth. And it seems like they're out in space, and they technically are, but that doesn't mean it's empty up there. They're actually in the atmosphere. They are in a very thin part of the atmosphere called the exosphere. There is enough up there to cause drag. About every 2 months, the International Space Station has to reboost, where one of the capsules that's attached, right now it's the Soyuz capsules that do this. I suspect SpaceX might start doing it too. Will use its engines. The station doesn't have any engines of its own, rocket engines, but we'll use the engines on these capsules to boost it up to a higher orbit. and it starts inching back down as atmospheric drag slows it down. So it's something we have to do all the time. This takes that into account so we can really predict over the next couple of days what might happen. And then the last part is all about error checking. The counter here, that goes up every time this gets published. It's several times a day. Some satellites, they'll publish their orbits a couple times a week at most. Anything with people on it, we're a little more careful on. We want to make sure we know exactly where it is so that it can be avoided should there be any problems. This is all published by the US Air Force. The Air Force is responsible for tracking anything larger than a softball. The ISS is definitely larger than a softball. It's about living space, about the size of a 3-bedroom house. And if we were to bring it down and set it down on Earth, it would fit pretty well on a football field, just to give you some scope. So let's jump in. I'm going to switch over to something called Google Collaboratory. If you're just learning how to code, this is a great place to start. It's free. You just need a Google account, and you can go in and start typing away and run your code. It saves it. You can go back to it later. You can save different files and work on different lessons you're working on. Completely free. What's happening on the background is Google is standing up a virtual Linux box, a virtual Linux machine just for you that will run this code. And after you leave it for a while, they recycle that and let somebody else use it. So I'll drain this. We'll go step by step, and we're going to answer the question of when is the space station going to be next over my house? I've been doing this long enough to know that live demos sometimes can go sideways. We'll hope it doesn't today, but if it does, we'll deal with it. So section by section. This first section, you've seen this before from Skyfield. Import these couple of things. Load is how I load things from JPL. WGS84 is it describes longitude and latitude on the Earth's surface, so I'll need to have that. This is Pi time zone. We'll need that to convert from UTC back into Eastern time, so we can make good use of that. Matplotlib, I probably don't need that. I can probably get rid of that. I mentioned timescales. You'll see this over and over again in this code. What we're going to specify a timescale, a start and an end time for when we want to measure where the station is and whether we can see it or not. And I'm going to go ahead and use this WGS84, and that's the latitude and longitude for Raleigh. Since we're talking about stuff in the sky and when it might be coming over the horizon, I'm going to go ahead and specify the elevation. You'll notice throughout this code, I'm using meters here. I'm not using feet. I'm not using miles. I can convert things back into miles. You can't get anything but metric out of Skyfield. If I want to describe something in miles, I have to do the math myself. Skyfield is a scientific package. Science uses metric code or metric units. I'm hoping one day the United States will all be on metric. That's probably not going to happen anytime soon, but scientists always use metric. So I'll run this. And you see, I've already run it previously, so all these things have been installed. This right here is unique to the way Google Collaboratory works. It is a way to install something that's not necessarily on Google's servers. It goes out to actually to GitHub and pulls in Skyfield from there and does the installation. That's all done. So let's go ahead and pull in the information about that two or three line element set that I showed you previously. We're going to pull that from a resource called Celestrak, and I'll show you what that looks like. This is what all of the space stations, well, actually, this is the entire catalog, the entire Spacetrack catalog. So these are things that are currently up there. Vanguard 1 is a satellite. It's one of the first satellites that was ever launched. This was launched back in the late 50s. And it's still up there. It will probably be up there for another 50 some years. But if we run this, it loaded 69 satellites. I'm picking just the International Space Stations. Just the International Space Stations and things that are related to it. So let me show you what that actually looks like. Let's mess out of the way. So there's the one we're most concerned with, ISS Zara. And there is 21030. So that's yesterday at noon is what is published there. I've loaded 69 of them. But as we can see, there's a ton of them here. All these are AeroCube, Lemur, stars. These are all satellites that have been deployed by the International Space Station. Here's some ISS debris, so on and so forth. They're all tracked under that. The only one we care about is ISS Zara. Zara is the name of the first module that was launched 20 years ago, and we track the whole station based on that one, if you're wondering what that means. So back to here, we're going to select just ISS Zara, and we can see from here that it's number 25544. That's good. The epoch was when this was measured. These orbital elements were measured, was back yesterday at noon UTC. And let's see where the space station is right now. And I'm going to use a NASA resource that also uses a European Space Agency resource called Spot the Station. This will take a couple of seconds to load, but it's going to tell us exactly where the space station is. All right, so it's just crossed into night in Western Europe. So let's keep that in mind, that right there. I'm going to go back over here, and I'm going to figure that out using Python, using these orbital elements that we just loaded. So my time is now. I'm going to do a geocentric because we're looking at where the point that the International Space Station is directly over. We want to get the longitude and latitude of that. So it's a geocentric observation. My subpoint, I want to see, again, where that is. I'm going to run it, and it tells me it is over latitude 51 point something, longitude 25 point something. And just by looking at these numbers, I know I'm probably on the right track. Positive latitude means we're in the northern hemisphere. Positive longitude means that we are west of 0, which is UTC, which is close to London. And hey, it's 265 miles above the Earth. That means they've reboosted recently. So let's take those numbers and let's click through to Google Earth, another resource on the web, just using things that are freely out there to check myself. Notice I'm not just writing the code and hoping that it works. I'm checking all along the way. That's called test-driven development. I'm a big, big proponent of that. I write things in test and then convert it into actual programs. So this will take a second to load as well. All right, and it zooms way in, so we're gonna have to zoom way back out. So that's the point it was directly over when we ran that code. So let's keep zooming out, zooming out. I can tell by the Cyrillic town names that we're probably in the Ukraine somewhere, or perhaps Russia. Zoom out, zoom out. I know this is really jerky on there, but I'll slow down in a moment. All right, and we'll twist it around a little bit. Come on, zoom back in. Okay, so we're in Western Europe, so we're doing pretty well there. So we know that our code is working pretty well to find the current position of the space station. But that's not the question that we wanted to ask. We want to know when the station is going to be in the sky. So I'm going to try a little different angle here, a little different option. I'm going to figure out where the station is topocentrically, again, using Raleigh. And I'm going to figure out the altitude, how high up it is in the sky, and the azimuth, which direction I need to face, north, south, east, west. And we'll go ahead and figure out how far away it is. And I'll do the math to figure out in miles because I don't want you to have to do the math yourself. So let's run that. So that tells me the altitude is negative 32 degrees. Well, if it's negative, we're not going to be able to see it because it's below the horizon. That makes sense because it's all the way over in Europe. 39 degrees, that makes sense. 90 degrees is due east, 0 degrees is due north. So 39 degrees, that's about where Europe is. That makes sense. And it is 4734 miles away. It's a lot more than 250 because it's not directly overhead. 250 will only work when it is directly overhead. So that's not much use to us. I can't see it that way. Let's go ahead and figure out when it is going to be in our sky. Again, we're using Raleigh. Here's our T0, T sub 0, T sub 1, start time, end time. I'm going to start today at midnight, and I'm going to end on the 5th, so a couple of days out. And we're going to find all the events where the station is above 10 degrees. So 10 is kind of a magic number, and it can vary for wherever you happen to be. If you're out at the beach, this number probably ought to be 0, especially if you're on the West Coast and you're seeing satellites rise from the west, because you have a horizon of 0. Here in the rest of the world, our horizon of 10 or 15 degrees, that's about where the houses or the trees or whatever are. So this sets a reasonable horizon, so we can expect wind to start looking for it. So what this does is it finds all those events, it tells me what the event is and the time the event occurs. I'm going to loop through those, and it's going to tell me when and the events are numbered. Event 0 is when it rises. Event 1 is culmination, or at its highest point, and then the event 2 is when it sets. We number things starting with 0. It just makes more sense that way. And I'm going to dump it out. This is a code that tells us what format I want the time in. So again, it's all stored in Julian dates in the computer, which are kind of hard to read. So I'll make it a little easier to read. I'm going to run it. Let's see what happens. Okay, so January 31st, 1800. So 6:30. Oh, let me scroll up a little bit. So at 1:43 UTC, it rose. It culminated 3 minutes later. It set another 3 minutes. It's a pretty good pass. So look at all of these passes. Now, if I go back and compare this to, so I'm going to test it against a known good, there's a resource called Heavens Above. And this is very, very similar to what's going on with your apps. There's nothing until the 2nd or 3rd of February. So why, when I look back here, do I see all of these passes that are happening today and tomorrow? Well, the reason is that we've asked it a question and it has answered our question, but we didn't ask it the right question. The question I ask here is, when is the space station going to be in our sky? Not can I see it? I can't see it because this is happening in the middle of the night, and some of these are happening in the middle of the day. We can only see satellites when it is dark here on the ground, but up 250 miles up where the station is orbiting, there's sunlight hitting it. And that happens for about an hour after sunset and an hour before sunrise. The way we tell that, the way we're able to filter out and just show the ones that are visible is we need to introduce our friend, the JPL ephemeris. We need to know where the sun is. So I'm going to go ahead and run this. This is loading the sun and the earth into the software. I've written a little function here that determines the position of the sun relative to where we are on Earth. And it's going to return that altitude, azimuth, and distance. I'm mostly concerned about the altitude here. So now I'm going to rerun this. And this time I'm only going to print out those passes where the sun is more than 12 degrees below the horizon, but less than 6 degrees above the horizon, or below the horizon. So that's that period after dusk, but before it gets too dark. So the station's going to be flying through its through sunlight, but it's dark enough here on Earth to find it or to be able to see it. So now a lot better. Now we're seeing the 2nd and the 4th. We're doing a lot better here, but still we're showing these times in UTC. Yeah, we can figure that out, but let's have the software do it for us. So here's kind of the final way of showing it. I set my horizon at 10 degrees again. I'm doing everything I did up here, -12 to -6, but this time I'm going to print it out a little bit differently. I'm using that pi TZ to convert the time zone. And now I've got something that's actually useful to me. I can see that I need to look for the station at 6:22 on February 2nd, and again at 6:23 on February 2nd. And I can tell from the difference between the start and the stop time, that's going to be a fairly decent pass, about 3 minutes long. And over here, this one's going to be really good. This one's 6 minutes. So that one's going to be really, really high in the sky. Some things I could add to this would be to output how high it's going to be, how high that altitude is. It might just skim across the top of the trees. That would be a very low altitude number. It might go directly over Raleigh, and that highest point might be 90 degrees up. So those are some things that I can add. I'm not actually finished here. I wouldn't, your apps and the on your phone and what you see online with NASA's Spot the Station or something like Heavens Above, they also take into account where that shadow is, because the station can actually appear in the sky or disappear, and you'll see it get brighter, 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 and then dim. What's happening is it's flying into or out of the Earth's shadow. I would need to consider that in here. I'm not done that yet, but this is just kind of a quick way to show you the process that I go through when I'm answering some of these questions. So I know that was a lot to take in, but I wanted to share some of the cool things we can do with this software and get you thinking about some of your own questions that you might want to answer, maybe with astronomy or maybe with some of the other sciences. And with that, I've got time for questions.
Thanks, Tony. So some questions from too long ago while you were finishing up with this portion. So Jeanne Murphy wanted to know, can these programs be imported to your phone and run from your phone?
Generally, no. There's going to be different languages that are used to create software for the phone. There's not a whole lot of Python that ends up on the phone, but the process is going to be the same, and you're definitely going to be the same, using the same resources. What you run on your phone is absolutely going to be using the NORAD elements. That's the only way to tell where the station's going to be at any point in time. Figuring out things about where the sun is in relationship to where you are. There's other algorithms that can be used to do that, and other packages to do some of the same thing. The fun thing is, as you start to learn some of the other languages, and we were talking about this earlier, my degree's in computer science, and when I went into college, I knew one, maybe two programming languages, was familiar with. I left college knowing probably 8 or 10, just learning along the way. Right now, I'd say I've probably been exposed, I know confidently probably about 20, and then I've been exposed to probably another 50 or 60 more. There's so many of them out there. You use the right tool for the job. JavaScript is not a great thing for this kind of coding, scientific coding. It's really good for presenting web pages, that kind of thing.
Okay.
But as you dig into it, you find out that solving the same problem, they end up going back to the same resources. There's a book sitting on my shelf that has all those algorithms to figure out things like where the sun is in relationship to your position on Earth.
So it's almost like your own dictionary, right, of terms that if you need.
Yeah, it is.
Your reference guide. Okay.
Exactly.
Okay, and then one more follow-up question about Python. Is it a compiled language, and can you make it an executable?
You can. It is primarily, though, an interpreted language.
Okay.
It is generally not compiled. There's some ways to compile it if you want to build up a piece of software and attach it to an email and send it to somebody that way.
Okay, thank you. And earlier, Jordan asked, why does the Air Force track the space station and not one of the space organizations itself?
The Air Force was tasked with doing this, and it is so that all the items are tracked. European Space Agency does some of their own tracking, but this is all shared amongst the different international organizations. Absolutely everything is tracked for safety reasons. We have had some, we call them conjunctions, where two things in space, be they a useful satellite or space junk, try to occupy the same space. That doesn't go very well. You have two objects in space that then turn into several thousand objects in space, and that's a bad thing. So you can kind of think of NORAD and what they're doing here as being like air traffic control. They need to know where everything is. And when something gets too close, the two organizations that own those two things, be it NASA or be it a company like Iridium that has communication satellites up there, or be it SpaceX with those thousands of Starlink satellites that are up there. And there was actually an incident a couple of months ago where one of the Starlink satellites almost hit a weather satellite. There's protocols involved, and somebody needs to move. It's not a game of chicken. You got to move, or bad things are going to happen. But it's the Air Force that's responsible for that air traffic control or space traffic control.
Thank you. And then Matt posted collab.research.google.com. Do you use this for most of your development, and how is it different from standard Python interface?
I mostly use, I've used a couple of different development environments. It's called an IDE, an integrated development environment. It allows me to put the code up in different windows. I can see output, I can see data files and things like that. The one I use right now is called PyCharm. There's a free version of it out there. I've also used Eclipse, which is a little more geared to Java, but it works okay for that. That's what I use most of the time. When I'm collaborating with somebody else, I might use Google Colab. I gave a talk a couple of months ago at the American Meteorological Society. I do a lot of work with the meteorologists here in North Carolina and around the country. And we did a talk on the accuracy of snowfall forecast. And I used Python and Matplotlib to overlay some of those forecasts to show, we were looking for, were we better at forecasting when we did it together, when we combined all of our knowledge? Absolutely, the answer is yes. But I was collaborating with another, he has a computer science degree, he also has a meteorology degree. We were able to collaborate on that code using Google Colab. That's its purpose.
Thank you. And then Philip asked, what's a good resource for finding different data sets we used?
I think it's called data.world. There's a couple of them out there. When it comes to astronomical resources, a lot of them are called out by Skyfield. A lot of them are supported by Skyfield. But when it comes to general data sets, boy, there's a lot of them out there. If you like mapping, the US Census Bureau has some great resources that you can pull down. If you're interested in the health sciences, there's a couple of websites out there that are specifically about some of the data sets that you can pull down. You can learn a lot just by playing with data and just by playing what if. That's the nice thing about Google Colab, is it's geared towards that what if. It's using something called an IPython notebook. And you saw me pressing play on those little triangles and breaking stuff into sections. You can go back and forth, change stuff, rerun it, try different options without having to run the whole code over again. So it's really good for playing with data and playing with the code.
Thank you. And earlier someone asked, Arca asked if there is a place they can follow more tutorials like this. And we commented that we hope to maybe do some more sessions like this with you in the future, but you're going to type in something else. Cool. Thank you. All right. So here's another resource for you. Yep.
Reddit's a great resource. Learn Python is a real nice subreddit. As there's new tutorials that are presented on YouTube, there's web pages. Some of them have spaces where you can go and type your code in, and as you're following along, run it right there. But that's a real good place to learn. The thing about learning a language is everybody learns it a little bit differently. Everybody has their ways of learning it. I like to be very hands-on. I like to try stuff. I don't like to just read it and try to take it in that way. So I gravitate towards those resources that are where you get your hands dirty. That works for me. That may not work for others. You may like to watch what other people are doing, watch them live coding, kind of like I've done here today, and see the results that way. Something like a Learn Python will give you lots of different choices, and you can pick what works for you.
Great, thank you. And then Jordan asked, and it looks like another student supported that question. As a high school student, is there a certain coding platform I should begin with? I've wanted to get into coding, but never had the chance to.
It depends on what you want to do. If you have a big interest in creating mobile applications for smartphones or whatever, Python might not be the best thing for you. If you're going to be more excited by creating a usable smartphone app, Java and there's some specific languages just for the iPhone, that might be a better option. But if you want to get involved in coding for science or just generalized learning how to code, Python's a great place to start. It's fairly easy compared to some of the other languages to get started in, and there's tons and tons and tons of resources. Something like a Learn Python, or the subreddits that have guidance on how to learn the language. There's lots of places you can get started with that. So I would definitely recommend, if you want some generalized programming experience or learn how to code in general, Python's a pretty good place to start.
Thank you.
More questions?
Just some follow-up comments from people in the chat.
Okay.
Matt says Python is today what Visual Basic was in the 90s, early 2000s.
Okay.
Yeah. So, and Jordan says that he started earlier as code.org, on code.org.
That's another good good resource. And there's some that are geared towards young ladies, girls that code. Don't forget that. And this is for everybody, young, old, male, female, doesn't matter. And I'll say that some of the best coders that I've worked with didn't have computer science degrees. One of the best engineers I ever worked with had a music degree. Music's math when you get right down to it, so it made a whole lot of sense. I worked with a great coder that had a history degree. So it's for everybody. And it can seem a little daunting at first, but you see how I broke my problems apart. You should do the same thing when you're learning. Don't try and boil the ocean. Don't try and do it all at once. You break it into little pieces, you solve little problems, and then you refine that problem to answer a better question each time.
And we talked earlier, Tony, talking about just how this is a language, right?
It is. It's like
learning a new language, and we can all learn to speak different languages, and you just have to practice.
You do, and that's a good analogy too, because I've done some things one way, but I can solve that same problem 6, 8, 10, 12 different ways, and it looks different, but it's solving the same problem. So even different programmers speak different dialects. And that's one of the challenges as a professional programmer, is maintaining other people's code, because they're speaking just a little bit differently than you do.
Well, we really appreciate you teaching us about this today, Tony. I learned a lot. I am not a coder, so this was really interesting to me. And I think that everyone in the audience really enjoyed it as well. And I'm going to share my screen, if that's okay with you. Absolutely. We have our closing slide for Astronomy Days today. And we are so thankful that you were able to join us today, all of you, in our last Sunday of Astronomy Days programming. Thank you for attending. Thank you so much for your time, Tony. And we are thankful for our sponsor, North Carolina Space Grant. We are thankful for the Friends of the Museum. If you would like to commemorate this virtual Astronomy Days, you can order your space gear at our store online at naturalsciences.org. And check out our recordings. They'll be available on the Astronomy Days webpage from our website later on next week. And thank you again. Have a wonderful rest of your day, everybody. Thanks again, Tony. And we'll sign off and say goodbye for this morning.